My name is Safirah from class A4 AS1203D. The topic that we choose for this presentation is Magnetism from chapter 6. Before we start, here is our group members: Siti, Norathirah, Hanis, Suehana, Siti, Suraya, and me myself, Safirah. Here are the list of the subtopics included for this chapter.
Hi, my name is Siti Norathirah. This is Yusmaili. So today I'm going to explain about the magnet and magnetic field. Okay, before I'm going to show you how to use the right hand rule, we need to know about the magnet first. A bar magnet is a source magnetic field that can be proven by moving a compass near the magnet. Magnet have two end poles called north and south. Like poles will repel and unlike pole will attract. Then to the right hand rule. Okay, this is an experiment shows that an electric current produces a magnetic field. The direction of a field given by right hand rule, thumb point along the direction current. The direction of a field given by right hand rule, okay, thumb point along the direction of the current, while other fingers give the direction of the field. An electric current flowing away from you produces a magnetic field that circulates in clockwise directions. A stationary charge particle doesn't interact with a static magnetic field. Okay, so this is the most important. When a charged particle is moving through the magnetic field, a magnetic force acts on it. So let's move on to the magnetic force. Okay, so this is the formula of magnetic force, where F is in newtons, Q in coulombs, and V in meter per second. Okay, so SI unit of magnetic field is Tesla or Weber per square. To determine the directions of force, we will use three options of hand rule. For the first one, the thumb is F, so this is I, and the other fingers are B. For the second hand rule, it is alternative to rule 1. Point your fingers in the direction of B with V coming out of your thumb. The magnetic force on the positive particle is in the direction you will push with your palm. And lastly, the third hand rule, where thumb as F, which is force, index finger as current, and middle finger as a magnetic field. Okay, consider positive charged particle moving in uniform magnetic field. By using right hand rule, the magnetic force is always toward the center of the circular part. Okay, because force produces the centripetal acceleration, we can equate its magnitude, QVB, in this case, to the mass of particle multiplied by the centripetal acceleration, which is V square over R.
Hi, I'm Suehana. I will continue present about magnetic field due to current. First, what is B? B is a magnet exerts a force on a current carrying wire. The direction of the force is given by a right hand rule, like this. The force on the wire depends on the current, the length of wire, the magnetic field, and its orientation. So the formula is magnetic force equal to current multiple length multiple magnetic field and multiple sin theta. Theta we can get from the angle between current and the magnetic field. So here is the summary of the right hand rules. When we have a long wire, we use the one option. Wrap your fingers around the wire with thumb pointing in direction of current. If the wire current go up like this, so point it like this, and then we will get the direction of magnetic field. When we bend here, this is the magnetic field. Okay, when we have the current and magnetic field, we can use this one. Fingers point straight along current, then bend along magnetic field. Then we will get the direction of force on the thumb. Here is the direction of force. Third, if we have velocity and magnetic field, we can use the same way as second by replace the current but with velocity. Magnetic field due to current divide to 2. First is loop and second is magnetic force. Let's look at loop first. This figure shows a magnetic field line due to a circular loop wire. right-hand corkscrew rule can be used to determine the magnetic field, like in this figure. This is the formula used to calculate the magnitude of the magnetic field at the center of a circular loop carrying current. Meanwhile, if it has coil, we can add N here. Next is current carrying wire. We also experience a magnetic force. Consider a long straight wire suspended in the region between the two magnetic poles. The magnitude of the total magnetic force on the wire of length is as follows. Total force equal force on each charge carrier multiple total number of carrier. Next is magnetic torque. The force on opposite side of a current loop will be equal and opposite. If the field make an angle with an perpendicular to the plane loop, we use this one. Torque equal to BIA sin theta. And lastly, if the torque makes turn, we can add N there, so it will be torque equal to BIAN sin theta.
Next, I will present about Ampere's law. What is Ampere's law? Ampere's law is the magnetic field in space around an electric current is proportional to the electric current which serves as its source, just as the electric field in space is proportional to the charge which serves as its source. Ampere's law states that for any closed loop path, the sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability times the electric current enclosed in the loop. Here is some example of application for Ampere's law. For this application, magnetic field of current. The magnetic field lines around a long wire which carries an electric current form concentric circles around the wire. The direction of the magnetic field is perpendicular to the wire and is in the direction the finger of your right hand would curl if you wrap them around the wire with your thumb in the direction of the current. The magnetic field of an infinitely long straight wire can be obtained by applying Ampere's law. The expression for the magnetic field is B equal to mu0 times I over 2 pi r. Next, I will explain about solenoid and toroid. What is solenoid? A solenoid is a kind of electromagnet created using a helical wire whose length is much larger than its diameter, which produce controlled magnetic fields. For toroid, a toroid is similar to a solenoid, but it's bent into a disc shape in order to close itself into a loop-like form. Solenoid field from Ampere's law. Taking a rectangular path about which to evaluate Ampere's law such that the length of the side parallel to the solenoid field is L, give a contribution BL inside the coil. The field is essentially perpendicular to the side of the path, giving negligible contribution. If the end is taken so far from the coil that the field is negligible, then the length inside the coil is dominant contribution. Here is some illustration of solenoid field. This is admittedly idealized case for Ampere's law give BL is equal to mu n times I, B equal to mu n over L times I. This turned out to be a good approximation for the solenoid field, particularly in the case of an iron core solenoid. Lastly, magnetic field of toroid. Finding the magnetic field inside a toroid is a good example of the power of Ampere's law. The current enclosed by the dashed line is just the number of loops times the current in each loop. Ampere's law then gives the magnetic field by B 2 pi r equal to mu n times I, B equal to mu n times I over 2 pi r. Tutorial is useful device used in everything from tape heads to tokamaks.
Okay, lastly is the application. There is a lot of complex application included of magnetism in our life, such as communication devices, magnetic levitation transport, wind turbine, and motor. Okay, that's all for our presentation video. Thank you.